Hello everyone, my name is Jigula Sharif. I am pursuing BTech second year in SRT in CSE B section. Today my PPT presentation is about greedy method, minimum cost spanning tree. Here is the outline for our PPT presentation. Introduction to minimum cost spanning tree. What is spanning tree? Properties of spanning trees. Introduction to greedy algorithms. Why use greedy for MCST? Prim's algorithm overview. Steps in Prim's algorithm. Examples of Prim's algorithm. Kruskal's algorithm overview. Steps in Kruskal's algorithm. Example of Kruskal's algorithm. Comparing Prim's and Kruskal's algorithm. Time complexity of Prim's algorithm. Applications of minimum cost spanning tree. Challenges with greedy algorithms and conclusion. In this slide, we are going to discuss about introduction to minimum cost spanning tree. A minimum cost spanning tree connects all vertices in a graph with the minimum total edge weight. It is essential in various applications like network design, circuit design. Understanding the greedy method helps in efficiently finding the MCST. What is a spanning tree? A spanning tree is a subgraph that includes all the vertices of a graph with the minimum number of edges. It must be acyclic and connected, ensuring there is a path between any two vertices. Every connected graph has at least one spanning tree. Moving forward to next slide, properties of spanning trees. A spanning tree for a graph with n vertices has exactly n minus 1 edges. Any edge added to spanning tree creates a cycle, violating the acyclic property. Different spanning tree can exist for the same graph depending on the edges chosen. Introduction to greedy algorithms. Greedy algorithms make the locally optimal choice at each stage to find a global optimum. They are often efficient than other approaches like dynamic programming. However, greedy methods do not always guarantee an optimal solution for all problems. Moving forward to next slide, why use greedy for MCST? The greedy approach offers a simple and efficient way to find the MCST. It builds the tree incrementally, ensuring that each step is locally optimal. Algorithms like Prim's and Kruskal's leverage the greedy technique efficiently. In this slide, we can see the Prim's algorithm overview. Prim's algorithm starts with a single vertex and grows the spanning tree one edge at a time. It always adds the minimum weight edge that connects a vertex in the tree to a vertex outside it. This process continues until all vertices are included in the spanning tree. Steps in Prim's algorithm. Initialize a tree with a starting vertex and no edges. Repeat until the tree includes all vertices. Choose the smallest edge connecting the tree to a new vertex. Add the chosen edge and vertex to the tree, updating the list of edges. In this slide, we can see the example of Prim's algorithm. Consider a weighted graph with vertices A, B, C, and D. Starting from vertex A, choose the minimum edge connecting to B, then C, and finally D. The resulting tree will have the minimum total weight. Moving forward to next slide, Kruskal's algorithm overview. Kruskal's algorithm sorts all the edges in the graph by their weight. It builds the spanning tree by adding the smallest edge and ensuring no cycles are formed. The process continues until there are n-1 edges in the tree. In this slide, we can see the steps of Kruskal's algorithm. Start with a forest, a set of trees where each vertex is a separate tree. Sort all edges in non-descending order of their weight. Add edges to the forest, ensuring no cycles until there are n-1 edges. Example of Kruskal's algorithm. Given edges A to B, A to C, B to D, C to D. With weights, sort them by weight. Begin with the smallest edge and add it to the tree unless it creates a cycle. Continue until the spanning tree is complete. Here we can see the spanning tree. Comparing Prim's and Kruskal's algorithm. Prim's algorithm is better suited for dense graphs with many edges. Kruskal's algorithm is more efficient for spare graphs with fewer edges. Both algorithms yield the same minimum cost spanning tree. Moving forward to the next slide. Time complexity of Prim's algorithm. The time complexity can vary based on the data structure used for the priority queue. This efficiency can Prim's algorithm makes suitable for different graph sizes. Time complexity of Kruskal's algorithm. Union find data structure operations can cycle detection add to the complexity. Kruskal's algorithm is efficient for graphs with fewer edges. Applications of minimum cost spanning tree. Minimum cost spanning tree are widely used in network design such as telecommunications and computer networks. They help minimize costs while ensuring all points are interconnected. Other applications including clustering and circuit designs in electronics. Moving forward to next slide. Challenges with greedy algorithms. Greedy algorithms may not yield optimal solution for all problems. Certain edge cases can lead to suboptimal results. It is crucial to analyze the problem characteristics before applying a greedy approach. In this slide, we can see the visualization of minimum cost spanning trees. Graph visualization tools can aid in understanding the MCST process. Animation of Prim's and Kruskal's algorithm enhances comprehension. Visual representation can clarify the decision making at each step. Here is the key points for our PPT presentation. Minimum cost spanning trees are vital for efficient network design and optimization. Both Prim's and Kruskal's algorithm utilize a greedy approach to find solutions. Understanding their difference and applications can improve problem solving skills. Let's end our PPT presentation with the conclusion. The greedy method is a powerful tool for solving the minimum cost spanning tree problem. Oneself with both Prim's and Kruskal's algorithm enhances algorithmic logic. Apply this concept to real-world problems for effective solutions. This outline provides a comprehensive overview of the topic suitable for the presentation format. Thank you. Have a nice day.